Yes. So today we will look at balance of linear momentum. So basically, this principle. So this is again one of the axioms, right, that we have adopted along with balance of mass. So balance of linear momentum, balance of angular momentum, first law of thermodynamics, second law of thermodynamics. So this is one of those axioms, right? And so what this says is that the rate of change of linear momentum, rate of change of linear momentum is equal to the sum of the forces that are acting. So again, this principle is to be applied to a material volume as usual. So that means, so suppose if now you have your material volume V0 in the reference configuration, now that goes to some V of t, that is in the deformed configuration. And so now we say that the rate of change of linear momentum for this material volume V of t is equal to the sum of the forces that are acting on this one. So first let us look at what are the types of forces that act on this V of t. Okay, so there are two types of forces that we will consider here. So that is first one. So types of forces. So one is body forces. So that we will take as B of x comma t. Okay? So that is basically the body force per unit mass. Okay? So this is body force per unit mass. Okay? And so so the total body force due to this B of x comma t will be integral of rho times B of x comma t times d over V of t. Right? So this is body force per unit mass. This is mass per unit volume times the volume, right? And so when you integrate that over the entire material volume, this is the total force, body force that is acting on the material volume. So some examples of body forces are gravity or electromagnetic forces and so on. Okay, so examples, gravity or centrifugal forces, right? Centrifugal forces. So and electromagnetic forces and so on and so forth. Okay, so we'll not go into all of them here. Then the second type of forces are surface forces. Okay, and so we'll call them as tractions. Okay. And so this surface forces, we need to make a hypothesis on this. So this tractions has the same units as pressure. Okay, so that is Newton per meter square. But unlike the pressure, it need not act in a direction that is normal to the surface. So you can say that pressure is a special case of tractions. So you can have tangential tractions. Okay, so that are also along the surface of the material volume. Okay, so let us state one hypothesis for, so this is known as the Cauchy hypothesis. So what it says is that there exists a traction field T of x T n due to the influence of the material outside of S of t. So, okay. So let us draw a picture. So what the hypothesis is basically saying is that suppose if this is the surface S of t, right? So this is your S of t, and then if suppose if this is the unit normal, and then there is a traction force T that is dependent on x, t, and n. So, so this is the hypothesis is that this traction, okay, which has the same units as pressure, acts on the surface and it is dependent on the position vector. So that is the position vector at this particular point on the surface, time t, and also on the normal. Okay, so see, usually all the other field variables that we have been considering so far, they depend only on the position and time. But this traction vector is different than these other field variables that we have been considering so far, in the sense that it is also dependent on the normal. So whenever you are talking of traction, you have to say on which plane that you are talking about, right? That's because or on which surface rather, not necessarily a plane, but on which surface it is acting. So that at that particular point you have to define what the normal is, and then this traction will be dependent on that normal also. Okay, so this hypothesis basically says that it doesn't depend on the curvature, for example. Okay, so curvature would be del dot n, for example, right? So these are two different surfaces that I have drawn at the same point, and you can see that they have different curvatures but the same normal. And so even though they have different curvatures, due to by this hypothesis, we say that the traction vector acting on both these surfaces at that point is the same. So hypothesis means it's like an axiom. That means we just adopt it to be true. We assume that it is true without trying to prove it. Okay, so this just like the balance of linear momentum is also an axiom, right? So we just assume it to be true, and then how do we verify whether a particular axiom is correct or not? So now clearly it is going to be impossible to cut a material inside and then figure out where the traction is pointing, correct? Because that is just not possible by any experimental means also. So the way to figure out whether a particular axiom is correct or not is to look at its consequences. Okay, so here we will adopt this axiom, and then we will see that the balance of linear momentum, okay, leads to a set of differential equations, okay, due to this hypothesis, and then we can solve those differential equations and then find out, let's say, the displacement field, stress field, and things like that. And that is something that we can match against experiments, right? And then if that matches against experiments, then we know that this starting hypothesis is correct. Okay, so and of course it has to stand the test of time also. So in the sense that it is possible that we adopt some axiom and then after some years we find that there is experimental evidence to say that that axiom is not correct. So that is also possible, but in this case this has stood the test of time, because this may have been proposed in, let's say, early 1800s or whatever it is, but it has led to conclusions that are consistent with the experiments. So we adopt this axiom, and now let us see what are the consequences of adopting this particular axiom. So first let us write down what we mean by this balance of linear momentum now. So this the rate of change of linear momentum, the integral of rho v times dv over v of t is equal to integral of t of x t n ds plus this is over s of t plus integral of rho v of x comma t times dv or v of t. This integral of rho v dv gives us the total linear momentum, okay, of the material volume. Then d by dt of that gives us the rate of change of linear momentum. And then we saw that T of xtn times ds, this will give us the total force on an element that is acting on this element ds. And then when you integrate it over the entire surface, that gives you the total surface force. And then similarly, this gives us the total body force. So the rate of change of linear momentum is equal to the sum of the forces. So that is the response. So we can write this equation in terms of the center of mass of the material volume. So let us just define what we mean by a center of mass. So define so center of mass of V of t is x bar, let us say x bar of t. So definition, so that is integral of rho x times dv over m, where m is the total mass within the material volume. So that is just rho times dv over v of t. So basically integral of rho x dv divided by the total mass that is contained within the material volume. Okay, so now we can write this particular statement as follows. So we'll just shift this here. Yes, so I can write this particular statement here. So that is m times x bar is equal to integral of rho x times dv. Now, if I differentiate this with respect to time, then I will get that m times x bar dot is equal to d by dt of integral of rho x dv, which is equal to integral of rho times dx by dt times dv, which is equal to integral of rho times v times dv or v of t. So this is over also v of t. So see here, m is a constant because the mass does not change with respect to time, and so there is no derivative with respect to time for the mass part of this relation. And then m times x bar dot is d by dt of this, and then here I am using the second transport here. So this is tt2, right? Second transport theorem. Then I get this, and then dx by dt we have seen that is just the velocity here, so that is what you get. Now, so mx bar double dot is equal to d by dt of integral of rho v times dv over v of t, and that is exactly this particular term. So you can also write this whole statement in terms of the motion of the center of mass. So you can write this as m times x bar double dot is equal to integral of t of x tn ds plus integral of rho v times x comma t times d. So you may have seen this particular relation in the context of rigid body mechanics, but now we are saying that this statement is true even for deformable body mechanics also. So right, because so suppose if your material volume is deforming like this. So suppose if this is your v of t, and then now it becomes some very weird shape, let us say, and then now this is your v of t. So suppose if your x bar is here somewhere, so this is your x bar, and so the mx bar double dot is given by the sum of the forces. So even if the material volume changes its shape and size, even then this particular statement is true. So whatever, so this is a generalization of what you may have learned in your rigid body dynamics class. It is not even necessary that this x bar should lie on the body. So it need not be a material point on the body, right? So suppose if I am looking at circular disc, right, hollow circular disc, right, like this. So then in that case, your x bar will be. So it can be a fictitious point also, right? The x bar will be at the center of that disc, so it can be a fictitious point. So it need not be a material point. Yes. So now we will state and prove an extremely important theorem, which is Cauchy's theorem. Okay, so basically this theorem gives us the relation between the traction vector and the stress tensor. So first, of course, we have to define what we mean by a stress tensor. So the definition of the stress tensor will also come out as part of the proof. And the second thing that comes out is the governing partial differential equation for the stress tensor, for the Cauchy stress tensor. So these are the two things that will come out of this particular theorem here. So this is a very, very important theorem. Let's look at that now. So, theorem. So, assuming that the So basically we assume that the body force and density and acceleration are continuous functions of x at any time, and we assume that the traction is continuously differentiable with respect to x. So what does this continuously differentiable mean? So basically it means that the function itself is continuous and its derivative is also continuous. Okay, so that is what we mean by continuously differentiable with respect to x for each n, and also it is continuous with respect to n. The balance of linear momentum is equivalent to the following two statements. So there exists a continuously differentiable, so again tau, this tau is continuous and its derivatives are also continuous. So that is what we mean by continuously differentiable, this tensor field. So this is the Cauchy stress. Okay, so this tau xt is the stress tensor that we are going to define, and the relation between the stress tensor and the traction vector is this: T of xtn is equal to tau of xt times n, and tau satisfies this. So basically the important conclusion from this theorem is that the traction depends linearly on the normal n, okay, through this mapping. This stress tensor, as you can see, is not dependent on the normal. Okay, so the dependence on the normal is made explicit via this theorem here, and this tau, which is the Cauchy stress tensor, satisfies this particular equation. So rho times acceleration, dv by dt is nothing but acceleration, is delta tau plus rho b. So remember that this divergence of the stress tensor is with respect to the spatial coordinate position. So that is, so as I said that, so this Cauchy stress tensor tau is the true stress that is experienced by the body. Okay, so in this course we are also going to define additional stress measures. Okay, like the first Pictorial stress and second Pictorial stress and so on. Okay, so although these other tensors, other stress tensors also have units of stress in the sense that they also have units of Newton per meter square, let us say. But they are in some sense fictitious quantities. Okay, so they are basically quantities that are defined on the reference configuration. Okay, especially the second Pictorial stress, for example. So that is something that is defined on the reference configuration, and it is just a purely mathematical object that is introduced in order to simplify the solution of boundary value problems. Okay, so I would not try to give any physical interpretation to this first Pictorial stress and second Pictorial stress. Okay, although they have the same units of stress. Okay, so we can think of them as mathematical entities that are introduced in order to solve boundary value problems. Okay, because it is convenient to introduce them. But this stress tensor tau is the actual stress that is experienced by the body in the deformed configuration. Okay, so that is the important thing to note here. So now let us look at the proof of this particular theorem. So yes, so proof. So this proof is again this tetrahedron. So this is the usual Cauchy tetrahedron proof. So this is A, B, C, and this is the origin O, and this is E1, E2, E3. So this is actually the global coordinate system is located somewhere, and this is actually just some position vector x. Okay, so this is your E1. So this is so basically we are considering some point. So this point is in the material volume, let us say, and so the position vector is x with respect to this global coordinate system. So these axes are just drawn them to be parallel to these E1, E2, E3. So that's one. But the actual coordinate system need not be located at this particular point that we are considering here. So I'm not going to go through the entire proof for this particular theorem because you have already studied this particular theorem in your earlier classes on solid mechanics. So I am just going to give a very brief sketch of the proof here. So basically we apply the balance of linear momentum to this tetrahedron here, right? So this, so if you write now this as rho times dv by dt minus v, that is equal to integral of t of x t n times ds over s of t plus integral of t of x t minus e1 times ds1, this is over s1, plus integral of t of x t, this should have been minus e1, sorry, and this should be minus e2 times ds2 over s2 plus integral of t x t minus e3 times ds3 over s3. Okay, so these, so this surface, so this ABC, which is the inclined surface of this tetrahedron, that I am just calling as S itself. So this ABC I am calling as S of t. Then this S1, that is OBC. OBC I am calling as S1. Then OAC I am calling as S2, and OAB I am calling as S3. So basically the normal to this surface is minus E1. So this 1 I am calling because the normal is minus E1. Then here the normal is minus E2, so I am calling this surface as S2, and here the normal is minus E3. So that is the reason I am calling it as the surface S3. So we are just, so here first I am using the second transport theorem. So the d by dt that was sitting outside the integral sign, I get it first inside, just like I showed you in the previous proof also. So here this is obtained by TT2. So this is the second transport theorem. And so the this is just the linear momentum minus the body force term. Okay, so the linear momentum or rate of change of linear momentum minus the body force term. So that is this is times dv. Okay, so this is times dv is equal to this. So we are taking this v of t to be this tetrahedron here. So that is what we are doing, and that is now equal to the sum of the surface forces that are acting, because body force we have already taken to the left hand side here. That one. So this is the traction that is acting on the inclined surface. So you can imagine this is the inclined surface, right, and this is the vertex O. Okay, so this is the surface S, and this is the vertex O, and then there are three planes, okay, that are along E1, E2, E2, E3, and E3, E1, right? So that is what is shown in the figure. Now the traction on this S1, because the normal is along minus E1, so that will be Tx t minus E1 times this, and so on, and similarly for the other surfaces. So this is your balance of linear momentum. Now what you do is that basically you shrink this tetrahedron to a point. Okay, so that means you let this inclined surface come towards the point O. So that is this point O. But when you are doing this, you have to keep the normal direction the same. Okay, so this normal should not change. So see this. So basically, this is your inclined surface S, let us say, and now I am just bringing it close without letting it change its orientation. So the normal N should remain the same when I am doing this shrinking procedure. So what will happen is that this volume integral that goes to 0. Okay, so the details are given in the book. So as I said that I am not going to go through the details because we have already seen these details. You have already seen these details in an earlier class. So I am not going to go through the details, but it's more like a revision of what you have already seen in that in other courses. So basically, when you shrink this to a particular point, then what you will get is that t of x t n is equal to minus of summation of t of x t minus ei times ni I equal to 1 to 3. So this I equal to 1 to 3 indicates the three phases S1, S2 and S3. Corresponding to that, this is the contribution to that, and this is the term from the inclined surface. Okay, so T of x Tn is related to the normals in this particular way here. The volume term goes to 0, okay, in the limit as your h tends to 0. So as I said that I am not going to go through all the details, but essentially this is what you will get, right? Now we will use the continuity of, so if you read the statement of the theorem, we have seen that the traction is assumed to be continuous with respect to the normal. Okay, so we can let the normal tend to E1. So let n tend to E1. So then what will happen is that your T of xt E1, right, is equal to, so E1 has components, so your n is now 1, 0, 0, right, because the E1 has these components. So n1 will be equal to 1, n2 will be equal to 0, and n3 will be equal to 0. Okay, so only the first term will have a non-zero contribution in this particular case. So you will get that this is equal to minus T of xt minus E1 times 1. So n1 is just 1. So you will get T xt E1 is minus T xt minus of E1. And then similarly, you will get that T of xt E2 is equal to minus T of xt minus E2, and T of xt E3 is equal to minus T of xt minus E3. So this is what you will get. Fine. Okay. So if you substitute all of these terms into this particular equation. Okay. So let us call this as 1. So substitute into 1. So substituting into 1. What you will get is that T of x Tn is equal to summation of T x T ei times ni. Okay, so this is from I equal to 1 to 3. So this is what you will get. Fine. Now we are in a position to state Newton's so-called third law, that is action and reaction law here. So from this, what you will see is that let us write what is T of xt minus n. Okay, so let us look at that. So if I substitute minus n there, so let me call this as 2 now. So let us call this as 2. So from 2 T of xt minus n is equal to minus of summation T of xt ei ni, right? Because ni will have the negative components minus ni. So this is what you will get. But this is nothing but this is equal to minus of t. So this is I equal to 1 to 3. This is nothing but T of x Tn itself, right? So T of xt minus n is minus of T of xtn. So this is nothing but the action and reaction principle basically. So let us draw it so that it becomes clear. So suppose there are two bodies that are in contact with each other. So let us call this point as with some position vector x. Now let us draw separated views at this point of contact here. So I am drawing the same thing, but just assume that now we are separating them out there, and here your normal is n, let us say, and then the traction vector is t that is acting. So this traction vector is due to the action of this particular surface at this particular point, because it is in contact with this particular point. This is the traction that this surface is exerting on this particular surface here. And so what this law is now saying is that now at the same point, okay, there is a, so this is now minus n, then there is an equal and opposite traction, so that is minus t. Okay, so this traction, if it is in this direction, there will be an equal and opposite traction that is exerted now by this body on this particular body at this particular point here. So this is the action and reaction, but if you see, I mean, in the way it is formulated in your undergraduate classes, it is not given very precisely, whereas here it is given a very precise statement. Okay, so there typically we are just dealing with flat surfaces and things like that, right? So here this can be any curved surface, and so what we are saying is that the traction, okay, so there I think we just say that forces are equal and opposite, but here actually it comes out in the form that the tractions are equal and opposite. Okay, so not the force, but the traction at every point is equal and opposite. Okay, at the point of contact here. So so suppose if it's a region of contact, then this law will be valid at every point along the contact zone. Yes. So this makes this Newton's third law very concrete. Okay, this whole statement here. Fine. So then let us move on now. Now we will define the Cauchy stress tensor. Okay, so this is an extremely important step now on the way here. So now define the Cauchy stress tensor. Define the Cauchy stress tensor tau of x or t as tau of x or t is summation of t of x t e k diagonal e k, or k equal to 1 to 3. Okay. So you define now the Cauchy stress tensor in this particular way. So immediately you can see that now there is no dependence on the normal. Okay, the way, because these are just the canonical basis vectors. These are just E1, E2, E3, which are the canonical basis vectors. So there is no dependence on n in this case, right? Now if you multiply this tau with n, then what do you get? So tau times n, times n is equal to integral, summation of k equal to 1 to 3 of t of x t e k times nk, because this nk is nothing but n dot ek. By the definition of the dyadic product, that is just n dot ek, so that is nk, and then this relation is exactly the same as this relation here, right? And that is nothing but t of x t n. So this is equal to t of x t n. Okay. So we have shown the first statement, we have proved the first statement in the theorem here, that t of xtn is equal to tau times n here. Right. Okay, so let's see. Okay, and then let us look at what are the components now of the stress tensor. So let us again write this stress tensor. Tau is equal to summation of k equal to 1 to 3 of t of x t e k dyadic e k. So this we have seen, and now let us write tau ij. So tau ij is equal to ei dot tau times ej. So these are the components of the stress tensor, and you will see that when you simplify this particular expression, you will get that this is equal to ti of x t Ej. Okay. So this is what will come out. So that is because, see, suppose if you take Ek times Ek dot Ej, that is so Ek dot Ej is equal to delta Jk, right? And then delta Jk will act like a substitution operator on this, so that will become J. So that is how you get Ti of xt Ej. Right? Okay, so yes, so this let's see. So yes, so let us try to draw a picture now to show the components of the stress tensor here. Okay, but before that, let me just say that T is equal to tau n, right? So T is equal to tau n. So here you can see that this is a the stress tensor here maps a vector to a vector, and also it's a linear transformation in the sense that tau acting on alpha n1 plus beta n2 will be equal to alpha times tau n1 plus beta times tau n2. So it basically is a second order tensor because it maps a vector to another vector and it's a linear transformation. So it's a second order tensor here. So okay, so now let us try to give a pictorial representation of the stress tensor here. Fine. Yes, so okay, so if I draw this block here, okay, and I will try to show the stress components also. This will be your this will be your tau 1. This will be your tau 1, and this is tau 2. This is your tau 2. And here this is tau p3, this is tau 1 3, and this is tau 2 3. So so let me just draw this here. So this is tau ij is Ti of x T E j. Okay, so now let us try to give a physical interpretation of the stress tensor components here. Okay, so actually, although I am drawing a block here, right? So this actually is just a device. Okay, so this is actually just three planes that are passing through the same point. Okay, so the position vector of this with respect to this coordinate system, let us call it as x, right? And so so these are actually, I mean, so the reason that we are showing this block is just for clarity. Okay, otherwise the picture will become very messy. But you have to remember that this block that I am showing has actually no dimensions. It is just actually, so this plane that I am showing here, I am showing it at a distance here. But actually that is not correct. Actually this plane is actually passing through the point x. Similarly, this plane is also passing through the same point x. And this plane is also passing through this point x here. And so now these are the traction vectors that are acting on that plane. So suppose if this is the plane that is passing through this particular point, then T1 is the traction that is acting on that particular surface. The reason I am putting 1 is because the normal to this surface is E1 here. Then similarly, this space has a normal E2 and the traction that is acting on it, let us call it as T2. And then this space that has a traction T3 similarly to that. Okay, and then now what you do is you resolve each of these traction components into each of these traction vectors into components along E1, E2 and E3. So this T1, let us resolve it into tau 11, tau 21 and tau 31. Then this T2, you are resolving it into tau 12, tau 22 and tau 32. And this T3, you are resolving it into tau 13, tau 23 and tau 33. So remember that this second index here, right? So that is actually representing the plane or the normal to the plane on which that stress component is acting, right? So here, see this second component is 1, this is 1, this is 1. That is because the normal to this particular face is E1. So that is why, so here you can see that the second component represents the normal to the surface on which the traction is acting. Okay, so this, so because the normal to this particular face is E1, so that is why the second component is 1. Then the normal to this particular face is along E2. So that is, so this index 2 is because the normal is acting, so the normal to this face is E2, and then similarly for this one. So you can see that this 3 represents the fact that E3 is the normal to this particular face. And then what about the first index? So the first index indicates the component, right? So this is the component of the traction vector along the E1 direction. So hence this is 1. Then it is the component of this traction vector along the 2 direction, E2 direction. So that is why this is 2. And then this is the component of that traction vector along the 3 direction. So that is 3. And then similarly for this one also. So this 1 represents the fact that it is the component of that traction along the 1 direction. This is the component of that traction along the 2 direction, and this is the component of the traction along the 3 direction. So this first index represents the component of that traction, right? Along which direction is that component? So that is what that represents. Okay, so and then we have not shown the stress components on the other faces. They will be equal and opposite, right? So our equilibrium will need them to be equal and opposite to these stress components here. So that that automatically follows. So this, as I said, is the actual stress that is acting on the body at that particular point. Okay, so this is the true stress. So Cauchy stress is the true stress which is experienced by the body due to the action of the forces that are acting on that particular body. So of course this is all at a point. So this is tau of xt means it is a stress at a given position vector x and at a given instant in time. So if you go to some other position vector and to some other time, of course the stress tensor will change. Okay, fine. So again, another important thing to remember is that suppose I want to find out now what the traction vector is on a given surface. So all I have to do is that I just have to multiply the stress at that particular point by the normal to that particular surface. So suppose I wanted to compute the traction on this particular surface. So suppose if the normal was n1, correct? Then the traction T1 would be equal to tau times n1. Okay. And suppose if I wanted to compute the traction on this particular surface, and suppose if the normal on this surface was n2, then the traction would be T2 is equal to tau times n2. So the tau itself is not changing, right? The stress at that particular point is not changing because that is a function only of x comma t. Correct? What I mean by not changing means that is not dependent on the normal. Okay, so that is just a function of x comma t, and that is getting multiplied by the normal, and then you will get the traction that is acting on that particular surface. So you can easily compute the traction now using this Cauchy principle, that tau is equal, t is equal to tau times n. Fine. Now we will use all these results now to derive the second result now. So that is this t is equal to tau n. We will simply substitute in the balance of linear momentum, and that will lead us to the governing differential equation. So let us look at that. So we will again write rho times dv by dt times dv. So this is just d by dt of integral rho v times dv. So this is transport theorem 2, right? Transport theorem 2. I can write it in this particular way here, and that is equal to integral of t of x t n times ds or s of t plus integral of rho b of x comma t times dv over v of t, right? This is, and now we will use this t is equal to tau n. Okay, I will substitute that here. So this is equal to integral of tau times n times ds over s of t plus integral of rho times b of x or t times dv. Now we can apply the divergence here to the first term. So I have already given you the recipe for converting from surface integrals to volume integrals. So that is, the recipe is del by del xi to ni. We have already seen this, right? So if you write this in initial notation as tau ij nj, then that will go to del tau ij by del xj, right? Which is nothing but del dot tau, the ith component of del dot tau. So this will be equal to integral del dot tau times dv over v of t plus integral of rho b of x comma t times dv. So I can club all these terms under one single integral. So I will get v of t. So here also I should have written v of t. So this is all v of t. So this v of t now rho times dv by dt minus del dot tau minus rho times v times dv is equal to 0. Right? And this is valid for all material volume. Right? So this is what we have always said, that basically we will use this arbitrariness of the material volume and use localization theorem. Right? So here, here maybe I was considering some material volume. We can consider any subset of that or any superset of that or some other choice. Right? Any material volume is possible. Right? And so this is valid for all v of t. And so that leads us to the governing set of governing partial differential equations. Yeah. So let us look at that. Now what we get? So we now get that rho times dv by dt is equal to del dot tau plus rho times v. So this is now the governing partial differential equation. So this is of course a vectorial equation, right? There are three components to this particular equation here, right? So this dv by dt you can also write as dv by dt. Of course you can write it as del v by del t plus del v times t. And so that is just a kinematical simplification of the acceleration. So you can always do that. Okay, so now actually you will see that this is going to be a very complicated set of partial differential equations, right? And these are all coupled partial differential equations, and so solving them is going to be fairly non-trivial. So that we are not going to consider at this particular stage here. But one important thing that I want to note here is that I have not said anything about the symmetry of the stress tensor so far, right? So this is just at this particular stage the stress tensor is unsymmetric, right? At this particular stage, but we will prove the symmetry of the stress tensor in the next class. So basically we have to invoke another axiom, right, which is the balance of angular momentum. So unless you adopt the balance of angular momentum as a separate axiom from the balance of linear momentum, you will not be able to show the symmetry of the stress tensor. So that itself shows that the balance of angular momentum is an independent axiom, okay, independent from the balance of linear momentum, right? So this So basically, it was a very enormous struggle for Euler. Okay, so Euler was the first person, I think, who formulated this balance of angular momentum as a separate axiom, and so as far as I believe, that it was a very big struggle for him also. I think probably like a decade. Just trying to determine whether this should be a separate axiom, because see, when we study mechanics of particles, then for a single particle, the balance of linear momentum implies balance of angular momentum, and balance of angular momentum implies balance of linear momentum. So if you talk about single particles, then these two axioms are not separate. But when we come to material volumes, and when we are talking of deformable bodies, then actually we have to adopt the balance of angular momentum as a separate axiom, and so that was not obvious. Okay, so that was not obvious. I mean, today we take all these things for granted, but at one stage it was very difficult to come up with all the correct axioms that govern deformable body mechanics. And as I said, that Euler was the person who was chiefly the one who formulated all these axioms in a very systematic mathematical framework. I mean, we sort of call them Newton's laws, but actually, if you see, if you read the history, it is actually Euler who formulated all these balance laws in a very systematic setting. Yeah. Okay, so this let me just write this out in Cartesian coordinates so that you get some idea about this. So this is rho times dv1 by dt is equal to del tau 1 by del x1 plus del tau 1 by del x2 plus del tau 1 by del x3 plus rho times v1, and then similarly rho times dv2 by dt is equal to del tau 1 by del this should be 2 by del x1 plus del tau 2 by del x2 plus del tau 3 by del x3 plus rho times v2. Okay, and then similarly you can write it for the third one also. So rho times dv3 by dt is equal to del tau 3 by del x1 plus del tau 3 by del x2 plus del tau 3 by del x3 plus rho times v3. Okay, so here, as you can see, that I am not assuming that this 3 is the same as 1 3, and similarly I am not assuming 2 is the same as 1 2, but they will all come out to be the same when we write the balance of angular momentum here. Okay, then the last thing for today is that see, so far we have shown that the balance of linear momentum implies the Cauchy principle, that is t is equal to tau n, and also the fact that tau satisfies this particular equation, balance of linear momentum equation. Conversely, if we say that t is equal to tau n and we adopt this particular equation, then that implies the balance of linear momentum. Okay, so let us look at that also. So yes. Conversely, now, if t is equal to tau n and rho dv by dt is equal to del dot tau plus rho b, then d by dt of integral of rho times v times dv is equal to rho times dv by dt times dt. So this is by the second transport theorem again. So this is tt2 and then now rho times dv by dt is del dot tau plus rho b. So this is equal to integral of so rho dv by dt is del dot tau plus rho times b times dv. And this you can again apply the divergence, So this will be tau times n times ds plus integral rho b times dv over v of t, and this is over s of tn. And this is nothing but the traction, right? So this is equal to, so let me just write it here. So this is, so this is nothing but the traction itself. So this can be written as, so this is equal to integral of t of ds or s of t plus integral of rho b times dv or v of t. Right? And so basically we have shown that the rate of change of linear momentum is equal to the sum of forces here. So the converse is also true. So of course the converse is much easier to prove because we are given these two statements. But so the harder part of the proof was of course that showing these two statements, starting from the axiom of balance of linear momentum here. Right? Okay, so probably in the next class we will show the symmetry of the stress tensor. But before that, I will again point out that again you have noticed that all our statements, they hold only for material volumes. Okay, so and one has to be very careful about that particular fact here. So you saw that even for the balance of linear momentum, we started out with this, right? So this is your n and this is your t and so on. Okay, so one cannot apply this balance of linear momentum to what is known as the control volume in fluid mechanics, at least directly. So suppose you have you are considering a fixed region of space, for example, and then there is some fluid that is entering this, and then there is some fluid that is leaving this control volume, let us say. So let us take that this is some fixed region of space instead of the fixed set of particles that we have been considering. Then you cannot now write for example, this particular statement here, that d by dt of, so let me just write it here. So you cannot write d by dt of integral of rho v times dv is equal to this. So suppose now this s and this v is now this material volume, this control volume now, and this s is this surface. So this is not correct. Okay, so this is wrong. I mean, you cannot. So basically, the point here is that we cannot apply the balance laws to a fixed region of space where material is entering and leaving. So these balance laws are applicable only to a material volume, and this is something which is very, very important. So one can derive an appropriate form for the control volume also, but it is not this particular form. So we can derive it. But so basically you have to go through some more steps before you can derive the appropriate form. Okay, so the control volume form, I will not go into that. Again, that is given in the book. You can take a look at it. But what I am trying to say is that will follow as a corollary of this particular statement. It is not at a fundamental level. All the balance laws are for material volumes. They are not for control volumes. Okay, and so any law or any mathematical rule that you see for control volumes is derived first from starting from the material volume, and then later as a corollary you will get the appropriate statement for a control volume. Okay. So with this we will stop here.